Hi everyone, welcome to the NASIO webinar on translating risk into action, preparing the electric grid for climate vulnerabilities. While people are trickling in, we are going to go over some housekeeping items. My name is Kirsten Verklas. I'm the Managing Director for Electricity and Energy Security at National Association of State Energy Officials, NASIO. And we want to thank the Department of Energy and specifically the Office of Electricity for their support of this series on risk and resilience. We had a few webinars across the fall, and if you're interested in listening to those recordings or see the slide deck, just reach out to the NASIO staff, either myself or Kelsey Jones. Next slide, please. So just before we get started, housekeeping items. You're all surely very familiar with the Virtual Meeting 101. This is a Zoom webinar, so only the presenters are going to be on screen. For any tech issues, please chat my colleague Kelsey Jones in the chat box or email her at kjones@nasio.org. Also, if you'd like to hear any of the recordings or webinar presentations from the fall. There will be time for Q&A at the end, so feel free to put your questions into the chat box or the Q&A box throughout the presentations, and we'll get to them at the end. And then just for your awareness, the presentation and the recording will be shared with the attendees and all the registrants after the meeting for your information. Next slide, please. So just quickly, we'll go over the agenda. I already did my opening remarks. I'm going to turn it over to Tony Morgan from Florida in just a minute, and then we hear from our excellent presenters who Tony will introduce. And then at the end, we will have Q&A. So again, thank you. Next slide is great. We're really excited about this webinar. As we're thinking about risk and resilience and how to prepare for climate vulnerabilities that are going to impact the electricity grid in the future and are already impacting it, as we've seen, unfortunately, throughout the weekend in Kentucky and Tennessee. We're thinking about all these kind of issues and are really excited to have three excellent speakers talking about all different components on climate vulnerabilities and the risk for the electricity sector today. And with that, I will turn it over to Tony Morgan, the Deputy Director at the Florida Department of Agriculture and Consumer Services, who will introduce our panels and be our moderator for today. Thank you to all who are joining us, and over to you, Tony.
Thanks, Kirsten. Once again, I'm Tony Morgan, Deputy Director for the Office of Energy here in the state of Florida, and I'll moderate this panel. And I'll just go ahead and introduce our wonderful speakers that we have here today. First up will be Emmanouil Anagnostou he's the Director of Eversource Energy Center. Next up will be John Gillis, Research Analyst from Argonne National Laboratory. And last will be David Wells, Senior Communications Technology Program Manager from Office of Electricity, U.S. Department of Energy. They will make their presentations. We will have about 15 minutes at the end of the presentations to ask questions. Please use, like Kirsten said, please utilize the chat box to ask your questions. So first up, Dr. Anagnostou, please go ahead.
Thank you, Tony. Good afternoon, everybody, and thanks for inviting us in this panel. I will be talking today about the work we do at the Eversource Energy Center at the University of Connecticut on outages, power grid outages, particularly focusing on the impact of storms on the distribution grid, and then using our predictive capabilities to evaluate how the resilience of the grid is changing under different infrastructure reinforcements, but also how the climate change could potentially affect this resilience. Next slide. So a few words about the Eversource Energy Center. It is a center that was established to provide science-based solutions and technologies on infrastructure resilience, particularly on the energy infrastructure resilience. We have 5 different research pillars: storm outage forecasting, tree and forest management, and electric grid hardening are the 3 very relevant to our talk today. But in addition to those, we're also looking into grid modernization as it pertains to renewable energy integration, the power grid, and cyber physical security issues, again, from DERs. and penetration of those in the power grid for functionality and security. We are a center that supports several research faculty at UConn and Connecticut. We have several faculty also in our staff, and we support students, and including undergraduate students in our research. So some of the work that you'll be seeing today are based on work that is done by our PhD students. Next. Okay, so this is the framework that I will be discussing today. And everything starts, obviously, when it comes to resilience by the weather. So we are dealing with trying to quantify first the high resolution variability of weather at space and time. And then we're looking at how that weather will interact, will interfere with the distribution grid and to a certain extent also the energy generation, power generation. When it comes to resilience assessment, though, what you see here is a distribution, I would say theoretical distribution, where if the x-axis represents, let's say, the severity of the impact, it can be number of outages in the power grid, could be the level of damage on the grid itself. You can see on the right side, transmission towers destroyed versus on the left, distributed grid affected by downed trees. So, of course, the larger the impact, the less frequent it is, and what the utilities or generally the infrastructure enforcement is trying to do is to push that distribution to the left. In other words, have less impact for the same amount of and severity of storms. Now, quantifying that shift in the distribution is the purpose of our study, and the way we're approaching it is through a hybrid modeling approach. One is using machine learning on the left, meaning for the parts of the distribution of the parts of the storms that are more frequent, and therefore machine learning can be trained to do a holistic dynamic evaluation of the response of the system to the impact of the storms, and then a more mechanistic type of approach on the more severe end on the right side of the forces, which is for direct impact on the infrastructure. Next. So a few words about the machine learning method we've developed. It's an output prediction model that integrates input from dynamic simulations or predictions from numerical weather model that runs for the Northeast, but it can be applied for any parts of the country. We are processing the data to generate weather parameters that are the most relevant to the infrastructure resilience, particularly winds, duration of winds above certain thresholds, flooding, precipitation intensity, soil moisture, etc. And we're integrating this weather with infrastructure information that comes either directly from utilities or indirectly from power lines or transportation or other data that we can get from other sources. At the same time, we have vegetation information and land cover information that will come from satellite remote sensing. In addition to this, we do have dynamic information on the leaves on trees because it's one of the components that converts, let's say, the strong winds into kinetic energy that affects both the vegetation as well as the damage to vegetation that can affect infrastructure. We integrate all this into multiple and different machine learning models that are trained based on historical outlets or damage data that, again, come either from utilities or observations. And then eventually, those machine learning outputs are integrated through some form of optimization to identify areas for a forecasted event where you're going to have extended outages or outages, let's say, within the power grid. We typically, the outages are lat-long, are based on a Cartesian grid, but we typically integrate those into areas like towns or counties where we can associate with different restoration activities. Next. So the model has been running for many years now, since 2016 operationally. We have processed more than 1,200 historical storms or events. This is based on 3 different states, 5 different service territories, and the typical error we find is around 40%. I should say that the models that we have developed are different for different storm types. That's one of the findings from our research, and we currently have models running for rain and severe rain and wind events, typically coming from extratropical storms. We also have different models tailored towards thunderstorms, winter events that's primarily snow-dominated or ice-dominated cases, and finally, severe events that are either major nor'easters or tropical cyclones that are affecting the Northeast. This different type of severities are actually identified based on the forecast, and eventually the right model is triggered for each storm in a forecasting model. For this, for the resilience assessment, and let me ask you to go to the next slide. We actually modify the model to work at the circuit level, meaning that we are actually predicting the number of outages for the entire circuit, for each circuit, let's say within a service territory, and each dot right now is the total number of outages for all circuits for all the events that we actually consider in this study. We used the extreme event model, the 450 events, and then we actually use the machine learning model to be trained with the enhanced tree trimming information that came from the utility itself. So now the model, in addition to all the other information I mentioned earlier, it actually is trained on how much trimming or enhanced tree trimming happened prior to each event that you see in this plot. So the model actually trained even better. You can see the improvement versus the previous version, where now trimming actually can help the model better characterize the variability of the outages. And actually, we see that in 2 different ways. This is in storm totals, and you can see that the scatter plot is within the 50% error. But also, as you can see here, this is different percentages when we group different circuits in different percentages of completed enhanced tree trimming. You can see how the actual prediction compares to the actual average number of outages per overhead line, and the model actually captures that change pretty well, which makes us very confident in applying it for resilience. Next. So the other approach, as I said in that early slide, is the mechanistic model. So on the other end, when we have very extreme winds, the primary cause of damages is direct effects, either from trees uprooted or direct impact on the infrastructure. And here you can see in a scatter plot the actual damages from failures, let's say, of poles that we receive from a utility versus the gas winds. And you can see that in gas winds below 50 miles an hour, somewhere in this range, there is no much direct relationship between gas and the damages. And that's why we're using machine learning, because this is the range where you have so many other combinations, so many other factors that are contributing to the damages, which a simple mechanistic model that is unidimensional, basically relating wind to damages, would not be able to characterize. But when you're actually pushing towards the very extremes, the very high wind conditions, hurricane level, or even tornado level, then you can see a pretty decent relationship that can also be explained by our mechanistic model. So So that gave us a confidence and say, well, what if we use the model, the machine learning model for all the events that are up to, let's say, 50 miles an hour. And then for the very extreme conditions, we are actually going to be switching to a more mechanistic approach where the machine learning actually fails because we have very little data to train it upon. So it's kind of, we're going to be a combined approach where we're going to be testing all kinds of weather conditions. And that allows us also to move towards the climate change where we're going to be experiencing higher wind conditions. Next. So I'm just going to show you one application of the model, and this is how we can apply it. So we use retrospectively, as I said, the prior 10 years of events, and we have about 170 events in this period. And we actually, since we had the model characterizing the tree trimming, so we actually set the trimming in the model to 0, meaning that going back in time, we removed any of the trimming that occurred in the service territory and used the model to predict how many outages would have occurred if we had not applied tree trimming. And if you can click again, next, yes, you will see that with the blue is the actual outages that were reported by the utility, and red is what the model predicts with the ETT. And as you can see, red and blue tend to actually follow each other pretty well. That means it's kind of not surprised there because the model is well trained. But the green then is the one that I set 0 to 0, the number of trimming. And you can see that as time goes, where actually the utility starts to perform cumulatively more and more tree trimming, you can see that the divergence from red becomes larger and larger over time. And I present that on the right side, where you can see now the divergence in recent years become much higher, almost close to 40%. And this correlates pretty well with the cumulative impact of enhanced tree trimming. And that's actually what can be used to quantify resilience, of course, into the future climate as well. Next. So the last thing I want to mention is how we can use the whole framework into evaluating the vulnerability. As I said, we applied that over several events over the past 10 years. But now we actually went back into the past 40 years, actually 45 years, using atmospheric reanalysis, continuous data since 1979. And we were able to actually simulate all the historic, all the outage events in the record of by using the outage prediction model. And that is now able to kind of map historical outages, and of course, the same framework can apply into a future climate projections, which can allow us to map future outages associated with the service territories that we are modeling. And if you go to next, you will see that from 1980 to 2020, kind of a plot that summarizes the severity of the outages that occur over the past 40 some plus years. And actually what you will see that about every 10 years in the past, we had kind of a jump in that cumulative increase of territory outages. And that is associated with the occurrence of a hurricane event. And but those changes were kind of in the range of 5 to 6 percentages. Now, if you look at just the past 10 years relative to the previous 40 years, we have experienced almost double the change in those cumulative outages, which indicates kind of an intensification of those increases of storm impacts in the service territory, just based on the actual data and the simulations we perform. Obviously, we're missing the future climate simulations that this particular plot can be extended to the next, let's say, 40, 50 years to see how those percent changes will actually evolve into future climates based on the climate projection that will come. And the last slide I have is summarizing what we've discussed today. As I said, one aspect that is missing here, and we're working actively, is to integrate the machine learning that I showed you earlier with the mechanistic models, because the extremes or redefining the extremes on the impact and severity it's very important, especially as we move into climate effects and climate change effects on the electric infrastructure. So this is an element that, of course, needs to also be looked at, not only for tree trimming, but a combination of many different resilience improvements. Tree trimming is just one of them, pole replacement, undergrounding, tree trimming, and other. It needs to be all combined into a single evaluation framework. And of course, one other element that we want to look at here is case studies of catastrophic events, let's say compound cases of hurricanes with flooding, and evaluating this through dynamic simulation. And with that, I conclude the presentation.
All right, Tony, you want me to jump in here?
Yeah, John, you can go ahead and go.
Excellent. Well, it's great to have the chance to speak with everybody today. My name is John Gillis. I'm a program manager at Argonne National Laboratory in the National Preparedness Analytics Center. The NPAC, our primary goal is to support state and local governments with decision-making tools, et cetera, to allow them to respond to emergency, disaster declarations, et cetera. I focus on energy in particular. And so what we're going to be talking about today is the state energy risk profiles, which we developed with DOE CSER. We'll talk a little bit about those, what they are, how to use them, where they can be applicable to you all right now. And then toward the end, I can just briefly mention a couple of things that Argonne's working on just to familiarize you all with our work. But we're good for next slide. So many of you may already be familiar with the state energy risk profiles. These profiles have been published before, and we've just now published our most recent version this year. So I think they were posted first in April, and then we made some revisions and reposted them again in the last couple of months here. Overall, there's 7-page documents that really describe the energy systems in each state, and then the hazards that impact those energy systems. And we'll walk through sort of step by step on those a little bit, but the goal is not to be entirely comprehensive, but it's to give you a quick reference, which is built from a whole lot of data that we've gotten from about 50 sources, to give you a quick reference to be able to look at things across the state, familiarize yourself, and then secondly, to figure out sort of the right questions that you might want to ask going forward. So next slide. So what is in these? When we talk about, there's really 2 resources here. There's on the one hand, data, which we've summarized mostly into sort of annualized costs and things like that, and then maps as well. So you can see the maps obviously below. When it comes to data, we've included information on generation, transmission, and consumption for electricity. We also have consumption information for oil and natural gas. We have some overviews of hazard impacts to those systems. Again, you want to be careful about what you can infer from those hazard impacts, because we're basically giving some summary information, but it gives you a chance to think about what you might want to look into further, and then looking further may help understand how is it that tornadoes or certain storms impact the electric system or impact the natural gas system, for example. We're also looking at oil and gas consumption data, and then hazards and also user error, especially when we get into the oil and gas sectors. We find that a lot of those operations require a lot of manual work, and so that leaves some room for error. Additionally, for maps, we have a map of electric sector assets at the transmission level. That's just to give you a good sense of how electricity moves around the state in a broad bulk power sense. Also, what kind of generation is in the state. And then petroleum and natural gas, we have pipelines and storage facilities, which again just gives you a sense of how is petroleum getting into the state, and it helps ask the right questions about what do supply chains look like, et cetera, in our state. Next slide, please. So just to give you an example looking at natural gas, here we're looking at the Pennsylvania profile, and you can see we have impacts to transportation assets. We have some information about consumption, and then just a little bit of summary information about how many gas processing facilities and LNG facilities you see. So how can you best use this? Again, I think you want to be careful drawing too many conclusions immediately from just looking at this, but what it might help you do is look and say, it looks like corrosion might be something that we might want to look into a little bit further and at least understand as part of our energy security assessment. We can think about what it means from a regulatory perspective. And then if you look to the right of that little graphic there, in Pennsylvania, you can see how many miles of transmission pipeline there are. And also, I think the age, although that might be on the next slide here. But so this is just to give you a good sense about the natural gas industry in your state, just in general. And if we go to the next slide, we can see also for oil. It'll be the same thing here. We'll look at petroleum in California. And again, we can look at losses due to transportation problems. We can also look at losses due to crude and refined operation problems, and then the causes of those. So this will give you an understanding of, for example, if you're engaging with stakeholders about challenges that they might have in their daily operations, you're coming in with a sense of how often does weather impact them, how much flaring is happening in the state. And you can see we'll give you information about, for example, on petroleum refineries, loss of containment or flaring. That's a leading cause nationwide. So it gives you a sense of, okay, we're sort of in line with the rest of the country, and it's not a unique thing to California, for example, here. Some examples of outside force. Yeah, so outside force is the sort of catch-all term, which might be anything to do with, for example, disruptions from digging or something like that. A lot of times you'll hear utilities talk a lot about misutility and making sure that you know where your pipes are before you dig, but that's a good example of outside force disruption. There are some other ones that in certain states, it's going to be less so the case from California, but landslides, for example, can be a fairly substantial one as well. Next slide. So what's not in the state risk profiles? This is important to highlight because we want to make sure that you're able to use the state risk profiles in the right way, but also ask the follow-on questions that we or others can help with, or that you can look into with your stakeholders in your community. So the state risk profiles don't have any state-specific or community-specific research. So what we've done is looked, and I'll show the data sources in just a second here, but we've summarized data from a vast number of sources, but they're basically national level data sets that we're able to roll up information from and describe for you here. So you want to be careful about assuming that when you see something that it means something specific for the state without looking a little bit further into it. A good example here is Illinois, which is where we are at Argonne. You can see floods cause a substantial amount of property damage every year in Illinois. This is a graphic that you'll find in the state risk profiles that just gives basically the annualized property damage cost. So that's helpful in illustrating that you may be curious about how is it that floods impact our energy infrastructure, but you can infer right away from this that it's an enormous impact on the energy infrastructure itself, maybe without engaging further. And that's because a lot of times utilities or energy service providers will have access to flood maps. They'll make sure to plan around those areas, et cetera. So this will give information that helps you ask the right questions, but it doesn't include studies specifically for a community that says Illinois has, for example, large electric losses due to floods. At the same time, it is helpful in sort of pointing you in the right direction. As you all know from this past weekend, tornadoes can cause significant damage, and they do often in Illinois as well. And so it will point you in the right direction at times. It helps kind of contextualize the environment, but we aren't giving you any specific information that we've studied individually, although we do have studies at Argonne that sometimes are able to facilitate on more in-depth analysis. Next slide. So where's the data come from? This is probably the most helpful slide in terms of understanding what the value of the state risk profiles are. As a lot of you know, you can get a lot of this data publicly, and we have, most of it actually comes from public sources. There are some subscription data sources that we use. We can always point you to those data sources. We can't release the actual data, but we can certainly send public data where we have it, or refer you to the right public places to get it. But we have data from 28 different sources and 50 different data sets. So the real benefit for you all is in order to get all of this roll-up information, it would take a lot of effort to try to comb through all these databases. So the state risk profiles are built to be a simple reference point to be able to look at basically a roll-up of 50 different data sets and understand what those data sets describe. What you will find, and the reason that we include the data sources in here, is that if you wanted to undertake a more thorough investigation, these data sets oftentimes have a lot of detail, and so it can be really helpful to look a bit further. So in addition to summarizing things in a way that makes it easy to quickly come up to speed on your state's energy environment, we also have references to all the data sources which are on the page that was linked earlier. And my contact information is at the end of this. If you're looking for something specific and you can't seem to find it, do always feel free to reach out. Even though I can't necessarily release data to you, for example, from Platts or hydrocarbon publishing. Platts is where we get most of the map data. Hydrocarbon publishing tells us about refinery outages and things like that. I can't necessarily release that data to you, but I can describe what's in the data set, give you a sense of whether or not it's something that would be an important subscription for your group. Next slide, please. So how best to use these? We've talked a little bit about that. I can talk about some ways that we know some states use them, as well as some ways that I use them even. The biggest way would be as a tear sheet. This is a great phrase that we've actually heard from several states, as a tear sheet to basically build a baseline understanding. So this is really characterizing the blue sky world for your state's energy infrastructure. You can understand kind of where it is generally, what impacts it generally. It's not a hazard by hazard deep analysis, but it gives you that baseline so that when something happens, you can understand what does that mean. It also can help address questions that are a little bit more specific, like are there certain areas particularly vulnerable to a hazard? If you're, for example, in the Chicago area, it's unlikely that floods come to mind first when we think about things that might be impacting community, but Illinois is a large state, so realizing that floods have a pretty substantial impact in the state is helpful to maybe point you toward things that you haven't considered before. You can also think about where is fuel storage. You can see the sort of bulk level fuel storage in the maps there, and then is it close to where we need it to be? If it's not necessarily a problem, and that's a good thing to keep coming back to, is if you see something, don't necessarily infer that if it doesn't align with what you think that it's a problem, but it helps you ask the right question. So for example, if you see lots of fuel storage in an area that doesn't seem relevant to where you might need to move it, you might ask, are there really good supply lines to get it to that area? Or are there trucking plans, et cetera? And that might help answer that question. And then finally, in general, it will help answer a question like how reliant is the state on a specific resource? A number of states you'll find that 50% of the gas consumed in the state is consumed by electric generation, and that's just 1% of the customers or something like that. So that gives you an idea about who's consuming your resource, what other resources are dependent on it, et cetera. This final note down here, these are really helpful sometimes if you're going to do a tabletop exercise, a grant application, a state resource or energy security plan. They're great attachments to add in because they can give a quick reference for people reviewing grant applications or folks that are sitting down for a TTX. Next slide. This is a very quick example about how I use them. So after Hurricane Ida came through Louisiana, my group was working on a response program for FEMA, and there was a need to understand the energy infrastructure in the region. I don't have much experience working in Louisiana previously, and so my first step was actually to go back to these state profiles. The goal of understanding how many investor-owned utilities are in Louisiana, how many municipal and electric ones, to look very generally at transmission corridors, and you can see one that I've kind of circled there. And these kind of became my pointers to think about, all right, what should I look further into? What should we pay attention to on the analysis? Who are the stakeholders that we need to reach out to? So it's a great, quick and easy reference to get you going in the right direction. It helped me very quickly understand the Louisiana environment and then delve a little bit further. And that's what they're probably best for and extremely useful for. So this is my contact information. Would love to have you reach out with any questions or concerns. Like I said, if you're looking for specific data, always great to have the opportunity to work on that with you as well.
Hey, David, you can go ahead.
Okay, hi. My video up? That's okay. Hi, my name is Dave Wells. I'm the Senior Communications Program Manager for Office of Electricity, AR&D Division, and ERD, which is the Transmission Planning Group of Office of Electricity. You know, Office of Electricity as DOE, you know, we provide leadership for the nation for reliable energy delivery. You know, we're all about the infrastructure, not so much about generation, but it's about how do we deliver the power and what goes into delivering the power. You know, we assist the lab with funding and then with help with developing technologies to improve the infrastructure, electricity into our homes, offices, and factories. We support development of federal and state electric policies, which is what we're helping you guys here with these webinars, to shape the electric system planning and operations, marketing operations. And we drive electric grid modernization, resiliency through research, funding, partnerships, modeling, and analytics. Next slide, please. So when you start looking at the emerging conditions that affect our power system, you know, the economics is driving the change to supply and load. It's about the customer load, how it's changing. Fuels that are used to generate. You know, right now the new administration are really leaning on renewables. But do we have to worry about what we're already using for, you know, our natural gas and for coal? You know, can't just walk away from it one day. You know, we have to look at how do we merge them in? How do we do a staged approach? You know, locations where electricity is generated. You know, means by which electricity generated is managed. How do we manage it? If we're doing DER, distributed energy reserves, we're using microgrids. How are we going to manage that? You know, characteristics for load served electricity, power system characteristics, they are evolving. You know, they're rational and are replaced by reduced stability, faster dynamics, transmission, distribution becoming more adaptive. You know, in the 20 years ago, we used to always use the thought that the electric grid looked like the water system, very large pipe and the multiple smaller pipes distributing out. That's the way it was 20 years ago. But now we got bidirectional flow. Now we've got people putting solar in their homes, businesses bringing solar and wind in their homes, and now they're wanting to sell power back to the industry. How are we going to adapt? You know, that's part of what we have to look at. Operator-based grid management and offline analysis. Just the old models and the old data just aren't sufficient. So operational contents is being challenged. Emerging threats, intense weather, as what this seminar is about. You know, how are we going to adapt with the changing weather, with the the extremes? That's what's happening. You know, in Kentucky. You know, hearts go out. You know, we got cyber and physical attacks, consumer expectations. They want more reliability and resilience. Look at what happened out in California with wildfires. We had more brownouts there than we saw 20 years ago. It happens. Next slide, please. So with all that said, you know, within OE, we started looking at modeling. We needed to facilitate understanding of complex data, large data sources. Demonstrate physics governing dynamics, not just hearsay. Estimate values of parameters that cannot be directly measured. Predict, simulate potential events and scenarios. Evaluate optimal resilience designs. Placement of energy storage, DER, solar and wind. Next slide, please. I know I'm walking through this very quickly, so I'm trying to get to the point here. With all that said, we went out and looked and said, we need a model. We need to be able to look the interdependency of electricity onto the grid and everything that goes along with that. With that said, we started the North American Energy Resilience Model. Our vision, rapidly predict the energy system interdependencies, consequences, responses, extreme events at national scale. Mission, develop and deploy engineering class modeling systems for planning and real-time resilience analysis. And key objectives to characterize partnerships with industry, labs, states, communities, and federal agencies to enhance coordination, support energy resilience. Next slide. So what does that mean? So we take the different domains. Now, we've only got 3 here. We've got the electric, natural gas, and communications. Since this slide, we've actually added railroads. We've added water systems, on top of these. So we take all these different layers, these 3 major layers. Sorry. And we take that and we then look at the domain behavior. What is the load? What is the ever-changing customer load? What are the domain components? What are the different regions? And then what are the threats? Next slide. So what does that give us? We collect the data, we process the data. We have 2 main groups within the NAERM, or actually 3. We have the long-range planning, which you can see up at the top of the corner there, national objectives. And that's where we're taking the different objectives, the threats, the code simulations for interdependency. We go through that. We put that through the system analysis, and we look at the real-time system data and nodes. That gives us some visualization. Now, either some of our federal agencies, as well as, some of our own OE and CSER, with Eagle Eye and the National Information Liaison, look at this data, and then we actually then can produce this and give you guys additional awareness to the state emergency operators, to FEMA, DHS, CISA, and all the first line responders. Next slide. So we just did a major study. We were a major part of the NERC FERC report done on the cold wave. And from that, we look at the simulations. So we're looking at natural, you look at the failures in natural gas, you look at the hydro, you look at the coal, you look at wind, we look at all 3 of those. Then we look at the geospatial boundaries, fuel types, the duration and the phase, amount of sensitivity and fuel type. What people didn't realize is that with the amount of storage that we had for natural gas, if that outage would have lasted more than another 4.5 hours, it would have been down for an additional 5 to 10 days, because we were that low on the storage from the natural gas as it was being used. So it's these multiple scenarios, and that's the NAERM is built around. Next slide. I know I'm burning through this quick. I want to show you I want to actually show you what the NAERM is. So we use a lot of different data sources. So coming out of this data source from this report, we used, unlike what Argonne, and let me back up a little bit. The NAERM is built up of 8 national labs, not just 1. We have 8. We've taken the expertise of each national lab, and they've taken a piece of the NAERM, and they all run it, and we run it very seamlessly. And Argonne is actually part of that. And they're our main one of our main experts in natural gas. So we had to look at most of our data go at the NAERM, and we're at about 90 different data sets now. And we have several that are real time. But what we actually most of our data is actually proprietary. It's coming from the utilities. It's coming from the natural gas operators. It's coming out of, you can get to the National Weather Service. We've got EIA data, but some of our data is actually proprietary because it's for load and it's for storage. We've got the EPA data on emissions on an hourly basis, but these are the ones that we were using to actually look at this study that we were asked to do for NERC and FERC. And so if you look on the sources on the left, and then you look at the gaps. Now, out of those gaps, we've actually already fixed about half of those gaps that we've actually got the data coming in, so that this year, when the next cold wave comes in, we'll actually have the data to actually be able to start giving, your emergency operating services and frontliners, giving them the ability to actually be able to work through and actually give you guys advanced warnings that maybe we can keep these outages. Can't stop them. Not going to stop Mother Nature. We can surely reduce the the intenseness of the actual outages. Next slide, please. So the NAERM, we developed it within the NAERM. We've developed co-simulations and predictive and reports that we actually are now starting to provide to the industry and to the emergency services groups. The first one we started was this spring, and we actually started out in June. And what it was developed for the wildfires. So we take our forecasted temps, fire index, national interagency fire centers, the wildlife risk tools. We examine the wildfires, we identify the forecast, we look at the drought and the fire potential, we compute the outage scenarios. We were able to actually produce and predict 5 fires before they actually started within 5 days. So if we can continue this is after the first year. So this whole next year, we're hoping to keep refining that, bringing it up to a better, even better percentage and actually do better predictions. Next slide. So here's some of the wildfires that we were looking at here. This was the wildfire risk projection. This is one of our 5 days that we did. We do this for five days in advance. We do a twice a week report. And we were given the on an anthropogenic and a transmission causes of the actual outages, as well as just coming out of the weather itself. Next slide. Let's give you examples of what we're going through here. So from our report, we were doing this, we did our report this year for the first time. We did it from July up through the 1st of November. So we gave the national temperature and wildfire potential. We gave the active and forecasted wildfire impacts on the grid. And the grid is not just the grid, it's the grid and the interdependency. So it was the comms, the natural gas, as well as transmission, and in some cases, distribution. Next slide. So here's where we're getting the report. Here's the natural gas comms and the VES. So we are actually showing the fires. So we had the Jack fire. This is an example of the bootleg and the salt fire, but it actually we gave the sub transmission line, the substation that were affected, and then what needed to be fixed. Next slide. This one actually gives you the alerts, and then on top of it shows you the actual areas within the alert, and then shows you the highest risks that are going through there. Next slide. Oh. Okay, looks like part of my slides. I'll tell you what I'll do. The other half of the slides were about the rest of our new report comes out starting in January, which will be our cold wave report. Cold wave report will be going over to Eagle Eye National Liaisons. It'll show the FEMA areas. It'll show it'll show you the ice index, as well as cold weather, wind, and snow forecast coming out, and then the effects that it will have on the grid as it goes through. I'm going to show my screen here and bring up the NAERM. Oh, it stopped. Okay. Sorry, everybody. There we go.
David, we could send those
I got it
around
right here.
after the webinar.
It should come up now. You should see it now.
Yes, we see it.
Okay. So this is the NAERM. This is what we look at. as you can see, you've got all these different areas in here. So we can look at, that we can look at the branches. So to give you an example of what we do here, here's branches within here. We can look at, wind and solar. And you start to think, what's the big deal with that? Well, some of the big deal with this is simply this, is we can look at things like, so here we can look at P&M. We know exactly what data is coming in, and we can do co-simulations with this. So we can look at solar, we can look at wind, we can look at the transmission lines. If you guys are looking to plan more lines, we can tell you exactly where to put them, where you've got transmission lines close to it, reducing the amount from years to, to less than a year of getting them installed, because you're not having to go out and put in permitting to bring transmission to the areas. We have all that data in here already. So what everything I'm gleaning over is areas that you can actually do the co-sim in. When we start looking at references, I can look at the roads. One of the ones that we've been working on lately is we're actually looking at evacuation routes. And what we're looking for is, when you look at evacuation routes, we're looking at what is the energy penetration for the emergency route. If we had 5 or 10% darn it, come on, let my mouse work. If we can actually start now to bring up the emergency evacuation routes here. So if I look at the emergency evacuation routes, in the next week, we'll have all the charging stations throughout the United States on our power grid, as well as showing these routes. So if I go 10% more EV or electrify our transport, do we have enough energy to actually support these emergency routes if there's an emergency? With gas, you bring in portable trucks, you can put them on the roads, you can keep people running. What do you do in electricity? How do you get power into them? These are the kind of things that we do in our co-sims within the NAERM that you normally don't see in most systems. Why? Because we have more than 90 different sets of data, because we have these interdependencies already built in. So that's why I want to bring some of this up. When you start looking at natural gas, we've got all the natural gas in here. So when I want to start looking at natural gas, I can look at it and say, okay, my natural gas, where am I sitting with that?
Thank you, David. I think this is great. I want to make sure we have a few more minutes for
I'm
Q&A.
sorry. So I just want to give everybody an update on that. But I mean, basically what we've got today is the NAERM is a large tool that that emergency operators could actually come to the NAERM. And the thing is, we're not state-based. This is across the United States. So you've got bordering states, some of these interstate pipelines or intra-state pipelines. If you need to know information about that, or some of the transmission corridors that are running along some of the states, these are areas that you can actually come to us. We can actually then take and run the co-simulations for you and give you these modeling scenarios for you. And we can do it on a geospatial basis, so that we're not getting out of your state and giving you information from other states that they may not want out.
Okay. Well, I want to turn it over to Tony, because I know there are a few questions.
Sure.
How many questions do you think we can do, Kirsten?
Maybe 2.
Okay. Well, let me do this question first for the group. How can states engage with the work being done at DOE, national labs, in organizations like Eversource Energy Center? Like, how can we engage with you guys?
Well, I know through our TIP, our ERD division within OE, I know that we are already working with the states, and from there we can actually help set up projects or set up, reports that need to be done, or surveys or studies, and then we can actually go out and help the national labs then deploy that.
Yeah, from the Eversource Center perspective, this is a university center. Everything we actually generate is open source data. The models also, they're published and so people can have access to our resources. A lot of what we do, obviously, David actually mentioned that we use utility sensitive information. So when it comes to case studies, we cannot share utility data, but we can tailor the models and the prediction tools to more publicly available data sets. They mentioned about Eagle Eye. We actually access different data sets similar to, it's kind of scraped over the net, over the internet, where they report all the customer outages, and we train the models on those data sets that are not sensitive to utilities, and we approximate then, or we proxy utility infrastructure information using let's say transportation networks, etc. So there are ways around utility sensitive data to scale up and generalize those kind of frameworks to other other states or other regions.
Tony, from the Argonne side, our group works a lot with state and local governments and supporting state and local governments. So through our regular working relationship with DOE CSER, there's a lot of room for me to be able to jump on calls and support sort of quick requests or information requests, looking for data, things like that. If you're interested in something larger, we do studies for states or for independent system operators, groups like that. And we're glad to sort of talk further about specific state needs, but on shorter things, I can definitely always schedule some time, and I'm always happy to support states as needed.
Thank you. One last question, I guess, it came from the question and answer chat box. Man, please have your thoughts on how this kind of advanced warning system may influence volatility in the electricity and natural gas markets. I think that's a question for David.
Yeah. Well, what it does, what it will do is, the biggest thing about it is you're not going to stop Mother Nature. What it does do is two things. One, the advanced warning gives the emergency operators more time. It gives them more time to repair. So one of the people that uses the NAERM is our PMA, our Power Marketing Authority, because they're a FED. And what they're getting ready to use, what they asked us for, was the ICE index, and that's a big one for them. In our SWAPA area, their biggest concern in the winter is ice. The fact that we can now actually give them information that says you're going to be seeing an ice storm. They can now send trucks out, get them remote, get them out there in areas that they know that are going to be prone to be getting icing and be having issues, get them staged, get the material out there so that after the event happens, they can get the system up that much faster. So it's about getting you more resilient, getting you back up and running. The other side of it is, remember, all this data that we're showing for the advanced warning is also in a COSIM. So we can actually run reports. You can actually run reports. We're in co-simulation models so that you can actually start overbuilding or maybe changing some of the way that you're configured. So maybe you can lessen the impact and severity of one of these events as they happen.
Thank you guys for all you've done in your presentations. I'll turn it over to you, Kirsten, for closing remarks.
Great, thank you. And I know John has to jump, so thank you to our excellent panelists, David, John, Emmanouil, our fearless moderator, Tony, and to all of you who stuck it out for this hour with us. I think these are great tools to evaluate some of the risks that the electricity grid is facing now and in the future, and we're happy to facilitate any connection to our speakers and to how you all can leverage these tools. So with that, thank you again, Office of Electricity, for supporting us, CSER for being always part of our endeavors, and to all of you and the panelists. And with that, have a great rest of the afternoon or morning, wherever you joined us from.